Hello, everyone, and thank you so much to CodeBeam organizers for selecting my talk. And of course, thank you for attending my session. It's a great honor to share our research activity with CodeBeam community. My talk title is Rclex, a library for robotics meet Elixir. Let me introduce myself. My name is Hideki Takase, but my account on Twitter, GitHub, and Slack workspace is Takase Hideki. It is my name in Japanese order. So I am an associate professor at the Kyoto University, the University of Tokyo, and researcher at the postdoc program JST. And also I am one of the co-leader of NervesJP. NervesJP is a user and developer community of NervS in Japan. At present, almost 200 people join this community from all over Japan, and some Japanese-speaking people join from overseas. We hold an online meetup about once a month. Please join our community if you can speak Japanese or you are interested in activity about NervS in Japan. So first of all, I would like to introduce ROS, that stands for Robot Operating Systems for Beam Community. ROS is a design platform to accelerate the development of robot systems. This is one of the most famous pictures that expresses the concept of ROS. There is 4 features for ROS: plumbing, tools, capabilities, and ecosystems. Plumbing means a messaging infrastructure for robot systems. Note that ROS is not an operating system, but a middleware for publish-subscribe communication. ROS provides powerful tools to support configuring and debugging the project and simulating and visualizing robot systems. Since robots will be operated in real physical world, it is very important to be able to efficiently simulate the physical behavior of the robot in 3D space, as shown in this figure. Capability means a broad collection of libraries. I will explain the detail of capability in the next slide. Finally, ROS project is organized by the worldwide open source community. ROS offers a broad collection of libraries that implement useful robot functionality, such as sensing, controlling, manipulating, and SLAM. They are expressed as packages in the ROS platform. Over 2,000 packages have been available as open source. We can use these packages to realize your robot systems. ROS packages can be installed by apt-get, and they can be built into your project by Colcon. Colcon is a project management tool based on CMake. They can enhance the reusability of existing design resources. We can realize component-based approach for robot system development. Plumbing is the most important feature in ROS. As a plumbing feature, ROS provides pub/sub-based asynchronous communication mechanism as a middleware. It is designed to support the quick and easy construction of distributed computing systems. The computational unit in ROS application is expressed as node. ROS nodes can communicate their data through a topic. ROS application can be developed by combining nodes such as a camera or a controller or a LED or a motor, and so on. Any nodes can publish its messages, and any nodes can subscribe messages by specifying topic name and message type. ROS employs data distribution service, DDS, as a communication layer. The benefit of programming is that we can construct loosely coupled architecture for constructing robot systems. A functionality can be updated by adding, deleting, or replacing a node. In addition, if a node crashes, it can be restarted independently. While pub/sub communication via topic performs asynchronous communication, service is also supported as synchronous communication. Action is a combination of topic and service communication, and parameter is key value store. Next, I explain the software structure of ROS2 in detail. Please note that there is two major versions for ROS, ROS1 and ROS2. From here, we will discuss about ROS2. The most important component in ROS2 is DDS. That is standardized by Object Management Group, OMG. DDS layer provides publish, subscribe communication functions, and also RTP's protocol in DDS can automatically search communication partner. The RMW layer, ROS middleware layer, is on top of the DDS layer. Since several vendors have already released high-quality DDS implementation, we can choose suitable implementation according to its features and license by changing this RMW layer. RCL, ROS Client Library, provides common functions for ROS2, including pub/sub communication, timer management, and so on. This layer is implemented in C. So we can implement a client library for any programming languages by calling this C layer. Currently, RCL-CPP for C++ and RCL-Py for Python 3 are officially supported. Rust, Java, Ada, Lisp, and more languages are also supported by this community. Okay, how does ROS work? Let's see the example code. This can help your understanding for robot programming with ROS2. This is a simple publisher node implemented by RCL-Py. In RCL-Py, the behavior of ROS node is developed as a class. The application first initializes ROS environment and creates a node from the defined class. Next, ROS node specifies its name. This is a token, and register itself with topic name and message type. This example specifies chatter as a topic name and string as a message type. And then ROS2 timer is created with create timer. This API needs to set callback function and timer interval. The ROS2 timer will execute the callback function at the specified intervals. In timer callback function, string typed message is prepared and published to chatter topics. By the way, what did you think when you saw the ROS system model? As I mentioned above, one of the most important benefits is that we can construct loosely coupled system by combining ROS nodes through the topic. I think it is like actor model. In the actor model, actors send and receive message in parallel to realize concurrent processing. All message exchanges are going to be processed asynchronously. Since the actor communicates only through the message, we can also realize loosely coupled systems with Alan and Elixir. So I believe actor model is suitable for robot systems. The fault tolerance from Alan could also contribute to robot systems. And more, I would like to suggest that robot programming should be functional. The concept of developing a robot by combining existing packages has a high affinity with the functional paradigm. So what we need is RCLEX. This is a new client library for Elixir. We have already published this library under Apache 2.0 license. It means that you can now acquire the power of ROS into the Elixir application. And you can now develop ROS nodes with Elixir and functional programming. But how did we realize RCLEX? And how do we communicate between RCL-CPP or RCL-PI nodes and RCLEX nodes? Key idea is very simple. We use NIFs, native implemented functions. As I mentioned above, the software structure of ROS is beautifully designed. So just we need to do is calling RCL functions via NIF from Elixir code. We built RCL.so static library to pack RCL functions and APIs with Elixir make. However, some additional techniques are also required to realize RCLEX. First, we need to convert Rn resource objects and RCL structures to each other. We added these conversion mechanisms into RCLEX. Second, RCLEX nodes are created as Rn processes. We need to design execution manager to handle the operation of PubSub functions. This manager is implemented with GenServer for now. Please note the difference between RCL-CPP or RCL-PI nodes and RCLEX nodes. RCL-CPP or RCL-PI nodes will be created as is for the Linux process. On contrary, RCLEX node will be created as Rn process. Therefore, RCLEX nodes will be much lighter than those of RCL-CPP and RCL-PI. So our objective of our research is to improve lost communication scalability with parallel processing of Rn lightweight processes. We suggest that RCLEX has two primary advantages. First, RCLEX can spawn a large number of lost nodes from Elixir code at the same time. Second, our execution manager realizes asynchronous execution between PubSub communication and their corresponding callbacks. Okay, please imagine that one node publishes message to the topic and another one node subscribes it. It is not a matter in C++ or Python. However, what happens when the number of publishing nodes increases more and more, and the number of subscribing nodes also increases more and more? In another case, there is a pair of publisher and subscriber nodes with one topic. But what will happen? The number of this pair increases more and more. We want to improve the scalability of such systems by using the power of Beam. This is a simple example code for publisher node implemented with RCLEX API. First, create nodes. API will create lost node with its name and the number of nodes. You can spawn massively lost nodes at the same time according to the value of num nodes. You can select the number of topics by the option of Create Publishers. When you select a single option, massively lost nodes will be published their messages to single topic. Also, selecting multi-option will create a corresponding number of topics according to the value of num nodes. Then you need to set callback function and its operation interval with RCLEX timer module. Please note that you can describe the node creation procedure with pipe operator. In the callback function, you can create the list of messages for each node efficiently by using Elixir enum library. Finally, you can publish message from lightweight Rclex nodes. We are happy if you feel this code is somewhat functional. So I want to show the demonstration of Rclex. I like this Japanese sentence, ron yori ran. The ran, it means the ran is mightier than the word. Even if you did not understand the explanation so far with my poor English, you will be able to find the impact of Rclex this demonstration. We used Raspberry Pi 4 with 4 GB memory for this demonstration. The distribution of ROS2 is Foxy. Foxy is the latest LTS distribution in ROS2. The left case consists of 100 publisher nodes implemented by C++ and 1 subscriber node by C++. In the right case, 100 publisher nodes are implemented by Elixir and Rclex. These graphs will show the history of CPU usage for each core. Okay, let's go. All nodes on both cases are spawning at the same time. Please see the left figure. When pub-sub communication starts, the CPU becomes so heavy, and even the graph could not be updated. And please see the right graph. At the start of communication, the CPU utilization becomes a little heavy to invoke RMVM and create nodes. But after that, the CPU usage will remain stable. This is the magic of Rclex. The development of Rclex is still in progress. We still have a lot to do to make Rclex practical. But we are confident that our continued progress will bring more benefits to both ROS developers and Elixir developers. We think that ROS developers will acquire better communication performance, especially in scalability with the power of Erlang. In addition, they will want to join Elixir and Erlang ecosystem to integrate their robot application with awesome framework and library such as Phoenix, NX, and Nerves. And also, we imagine that Elixir developers, including you, want to utilize OSS packages for ROS. Most of ROS packages and frameworks are implemented in C++ or Python. It makes little sense to implement them again in Elixir from now on. But we will acquire the benefit by combining existing ROS resources to your Elixir application. We could construct fault-tolerant and highly scalable robot IoT systems with both ROS and Elixir. Well, what I want to say at the last is, may the beam be with your robot. So wrapping up for my talk, I introduced our research activity for Rclex. That is a brand new library for robotics to meet Elixir. The source code of Rclex is published on GitHub. If you are interested in our activity, please give your star on our GitHub repository. And you can find our Hex package on HexPM. And also, we have already published Docker image that allows you to try Rclex just in 5 minutes. Please check it out. Unfortunately, there are many ongoing and upcoming works to do for Rclex. So if you can help our activity with your knowledge or skill, any issues and pull requests are very welcome. So thank you very much for joining my presentation.